So we were talking about estimation, and we had said that in general, for a parameter theta or a parameter vector theta, we define the log likelihood function as observation space of the d-dimensional observation vectors. Also have prior information about theta, then instead of using the maximum likelihood estimate, we can, or the maximum that maximizes fine. So this is the a likelihood function that we'll have to maximize, and the procedure will be similar. Now let's consider an example where yes. Yeah. Anyone wants to ask something? Devashish, you want to say something?
No, sir.
Okay. Just I heard some. Oh, sorry, I heard some incoming, so I just stopped. Yeah. Okay. Let's go back. Let's consider this example where xk equals some mu plus vector that the data points that we observe are xk's that are some mean plus relative white noise, relative white Gaussian noise with a covariance matrix sigma. And there is no prior information on mu. And want to use these samples estimate, and we want to use these samples to estimate mu. So first fine. And therefore sorry, this needs a slight correction. Yeah. So this is for xk, this is for xk, this is for xk, this is for xk. Now we have observed for has to account for these, and LMU has to account for all of these, and xk is minus b by 2, or rather this is simply minus half xk minus mu transpose sigma inverse xk minus mu and given d. Yes, does anyone want to ask anything?
So in the first line that you wrote,
Amit, yeah.
you wrote
Which
minus.
line? I'll just put my pen over there. Just point me to that. This line?
Sir, after estimate mu, yeah, this one,
Yeah.
just after to estimate mu. So this minus
Oh,
sign
yes.
will be
So,
there.
no. Sorry. Yes, this minus sign won't be there because this is the probability. It cannot be negative. Thank you.
Yes, sir.
Yeah. Yes. So, this is so L mu given xk and L of mu given d will be minus half summation k equal to 1 to capital N xk minus mu transpose sigma inverse xk minus mu. This is okay. Now this is what we have, or this is so. To maximize this with respect to mu, or we want to choose an estimate mu hat which maximizes this. So gradient L, gradient of L with respect to mu is minus half summation k equal to 1 to capital N. So minus half and half, so this is twice, and so this gets cancelled. Summation this and
Sir,
yeah.
for past 30 seconds, I cannot see what you're writing.
Okay. Oh, the share screen went
Yeah, just
went
share
off. Yeah, so share screen is on and recording is also on. That's good. So now can you see the screen? No.
Yeah.
Now you can see the screen. Yes, great. So you also see a recording notification, right?
Yep.
Yes, so this is fine.
Okay.
No, so just take some time. So you can now see what I have written.
Yeah.
And differentiating with this, so I essentially get a vector. So since I have to get a vector, basically get sigma inverse xk minus mu. Equivalently, this becomes minus sigma inverse outside within brackets k equal to 1 to n xk minus mu. Fine. And this is equal to 0. Or since sigma inverse cannot be 0, so you get this. So therefore xk minus mu summation k equal to 1 to n equals 0, or n mu equals summation k equal to 1 to n xk, or mu equals 1 over n summation k equal to 1 to n xk. Fine. Which is so this is called as the sample average. Okay. Now, another thing is that we want to know that whether this is the maximum or the minimum, because we want that the estimate should maximize the likelihood function. So I take the Hessian delta square mu of L. This becomes simply minus summation k equal to 1 to n sigma inverse equals minus n sigma inverse. Fine. So this is minus n sigma inverse. So now we know that from the properties of a Gaussian or from the properties of multivariate Gaussian random variables. I'll write this. Gaussian random variables, we know that covariance matrix is always positive definite. Since the covariance matrix is always positive definite, therefore minus of n sigma inverse is and equals summation k equal to 1 to n 1 over xk maximizes fine. So this is how we estimate, or this is how we estimate the mean of a set of observations. Now the question is, we have this mu hat. So estimates mu hat. So again, as I said earlier, mu hat equals R max search over mu. Fine. This is the mu has the value of mu that maximizes this function L mu. Now the question is that mu hat in itself is 1 over n k equal to 1 to n xk. So mu hat, the question is so yes, answers. Is mu hat the mean of xk, k goes from 1 to n? Someone tell me. Okay, there are just 4 of you. I can point at you and individually ask your opinion. Amit.
The formula is the same for mean, so I think it is. But the
So-
process by which we are getting is different.
Okay. Okay. So, yes, that is what Amit thinks. Devashish. Devashish.
I think it's correct.
Okay. Great. Siddharth.
Yes, the same. I also think that it is mean of X.
Okay. Anamitra.
Yes, sir, even I think this is the mean of XK.
Okay. Aditya, you have just joined or? So Amit left and Aditya joined or what? Aditya?
Yeah, I think it shows only 4 at a time, so that's why. Anyway.
Oh, it shows 4 at a time. Okay, you were here earlier.
Yeah, I was here.
Oh, that's strange. I thought it shows everyone.
No, because
So-
Amit is there right now, but it's not being shown.
That's strange. Okay. Cool. Anyway, so what do you think?
Yeah, sir. I think it is
Okay.
the mean.
Okay, so great. So we are unanimous in being wrong.
Lol.
So this is called the sample average, like I wrote earlier. And the mean is the expectation. This is the sample average, 1. 2, the mean is a deterministic quantity. The mean is a deterministic quantity, right? You know this is the mean. The mean of a random variable will be deterministic. Whereas this is the sum of n random variables. This is the sum of n random variables. And is itself fine. This is sum of n random variables and is itself a random variable. So mu is an unknown quantity or unknown stick. Mu is an unknown deterministic quantity and mu hat is the estimate of mu and is a random variable. Fine. So now since mu hat is a random variable and it is most likely different from
Sir?
mu. Yeah, Amit.
Sir, our objective is to minimize the difference between mu and mu hat.
Our objective is to find the most likely estimate of mu. Okay, minimizing the difference between mu and mu hat is a further goal that we'll try to achieve possibly today or in the next class.
Okay, sir.
Okay, that is a derived goal that we'll discuss. But anyway, mu is an unknown deterministic quantity and mu hat is an estimate of mu. Fine. So now let's define a third quantity, mu
Sir,
tilde. Yes.
According to law of large numbers, if you have a lot of samples, then shouldn't it converge to
If you have a
single
lot, if
value?
you have a lot of samples. If
So in that case, it's a random variable or a single value?
even in that case, it's a random variable. So we'll just look at its properties and answer your question. Okay.
Okay.
So I'll answer your questions in terms of the law of large numbers. But first, let's define mu tilde as mu minus mu hat. And we call this the estimation error. Fine. So this now let's talk about something that okay, so which way should I go? Let's first answer your question about the law of large numbers. So now since mu hat is RV and extension Gaussian, it is fully characterized by its mean and variance. Fine. So expected value of mu hat equals 1 upon n summation k equal to 1 to n. Expected value of xk equals 1 upon n sum k goes from 1 to n. Mu equals mu. So how is the call quality? I'm connected to the Wi-Fi and sitting next to the router. Whatever bad audio quality you are getting is due to maybe due to the bad IIT Wi-Fi. Yes. So coming back, so of mu hat equals expected value of or equals mu. So this is called an so an unbiased estimator is one where the mean value of the estimate is same as the quantity being fine. So now let's look at its variance. Expected value of mu hat squared, or let's look at its variance in one dimension, or that will make things clear in n dimensions as well. Mu is mu or scalar mu hat equals 1 upon n k equal to 1 to n xk.
Excuse me, sir.
Yeah.
Sir, can you minimize this meeting in general?
I had kept that just to remind me that everything is okay. So I'll minimize this. Everything is still okay. You can see the screen. You can hear me.
Yes, sir.
Excellent. Because earlier we have had accidents. Once I forgot to record. Once I was mute, and today you weren't able to see my screen. So I just wanted to keep this up here to let myself know that everything is fine.
Okay, sir.
So fine. This is this, and expected value of mu hat equals mu, and expected value of squared, because in a vector I would have had to derive the covariance matrix. That would be too lengthy. So let's not go into that, and this is easier to interpret. So this becomes 1 over n squared summation m equal to 1 to, or summation, since we are using k, summation k equal to 1 to n, summation l equal to 1 to n, xk xl equals 1 upon n squared summation k equal to 1 to n xk squared for k equal to l plus summation 1 upon n squared summation k equal to 1 to n summation l equal to 1 to n xk xl. So expectation I put here. Expectation I put here equals 1 upon n squared k equal to 1 to n value of xk squared plus 1 by n squared. Now these are IIT observations, as we have mentioned multiple times. N equal to 1 to n, L not equal to k, L not equal to k. Expected value of xk xl equals squared summation k equal to 1 to n, or rather simply is n times mu square plus sigma squared. The mean squared value is the square of mean plus the variance, right? Plus 1 upon n squared into n minus 1. Mean squared equals 1 by n squared into n squared mean squared plus 1 by n squared into n. Sigma square equals mu square plus sigma square by n. Therefore, variance of mu hat equals mu square plus sigma square by n minus mu square equals sigma square by n. So mu hat is a Gaussian random variable with mean mu and variance sigma square by n. Fine. So now say this is how the plot looks like for, so this is mean mu, and this is the standard deviation, right? So let's say this is how the plot looks like for 1. So n equals 10, say sigma square, or say let's call this sigma t, or rather the standard deviation, let me denote it as, say, what should I call it? The spread. Just for simplicity, let's call it tau. This tau is the spread. So since this tau is the spread, so tau equals sigma, n equals 10 means tau equals sigma by root over 10, sigma by 3. So fine. This is what happens. Then n equals 100. Tau equals sigma by 10. So essentially get something thinner. Okay, I made this big huge blue mistake. So let me correct this. And then obviously you'll get a, oh, sorry. For 1000, you'll essentially get a line like this. So the standard deviation essentially, so the sigma square or sigma actually represents spread around the mean. So this sigma is, or this tau in this case, represents the spread around the mean. The smaller tau, the less will be the spread around the mean. So as n tends to infinity, tau tends to 0, or as n tends to infinity, the mean is more and more, or the sample mean is more and more concentrated around the true mean. Or you can say that it converges asymptotically to the true mean. So as n tends to infinity, sample mean converges and you can say that also say that the rate of convergence is root over n. Fine. So Aditya, this answers your question?
I clearly answers, yeah.
Yeah, thank you. So this is how the estimate behaves. Now let's look at another example, another one dimension. So the estimate is a random variable and the estimation error consequently is another random variable. Fine. So now let's look at another example where we have a univariate Gaussian. So example 2. Variate Gaussian with unknown mean and variance. So there I say theta1 equals mu, theta2 equals sigma square, and pxk given theta. So these all of these are scalars equals minus 1 upon 2 pi root over 2 pi theta1 e to the power minus 1 upon 2 theta 2. Yeah, 1 upon theta 2 xk minus theta 1 square. Fine. And so the likelihood function is minus by 2 fine and minus xk minus theta 1 by theta 2 square since Since this is a random variable, theta 2 will necessarily be greater than 0. So multiplying on both sides by theta 2 minus n plus 1 upon theta 2 capital N. So this is a square, theta 1 whole square equals 0, or theta 2 or n theta 2 equals summation k equal to 1 to n xk minus theta 1 square, or theta 1. So can you theta 1 hat think theta 2 and theta 2 hat equals 1 upon n summation k equal to 1 to n xk minus theta 1. This is so you can estimate the mean and the variance, but let's try to find out the expectation of the variance or expectation of theta 2 hat. Theta 2 hat equals 1 upon n k equal to 1 to n xk square minus theta 1 hat square to xk theta 1 hat equals 1 upon n k equal to 1 to n xk square is mu sigma square plus as we have shown earlier minus now xk theta 1. Fine. Equals so 1 upon n xk square plus summation k equal to 1, L equal to 1 to n, L not equal to k xkxl equal. So taking its expected value, we get 1 upon n, or rather we again get mu k square plus sigma square by n. So substituting this, over here we get 2 k square plus sigma square by n. So now we'll use one good thing about whiteboard app. So sorry. So I'll just move it here. Yes. So no, this is not right. So I'll use this lasso again. Keep it here and possibly put this in a red box. So let's put this in a block of glitter. So this is something different. So this and this is 1 upon n oops. Summation k equal to 1 to n mu k square plus mu k square minus 2 mu k square plus sigma square minus plus sigma square by n minus 2 sigma square by n equals 1 upon n. And this is a constant, so 1 upon n, this summation get cancelled out. So this equals, so these get cancelled out, you get sigma squared into 1 minus 1 upon n equals n minus 1 by n sigma squared. So therefore, expected value of theta 2n equals n minus 1 by n sigma squared, and this is a biased estimate. This is what is called a biased estimate. So I think we can stop here and continue the next time. So any questions till this point? So no questions. Excellent. So then possibly we can disconnect and I'll upload this and everything as usual. So just Aditya, just a specific question. Anyone can answer this. Aditya, I want you to answer anyway. So are the images readable?
Readable.
Yeah, excellent. So everyone is getting them, right? You are sharing them on WhatsApp groups of your class and whatever.
Actually, the previous ones are not shared because everybody accesses Microsoft Teams directly to get them. So everybody is aware of that.
Oh, everyone is aware of these.
Yeah.
Excellent. Yeah, so my question was just that everyone is, because now the institute has made online learning an official policy.
Okay.
So my idea would be that as many people can attend these meetings, that's the best way, then the people who cannot attend the meetings can access the videos. The people who cannot access the videos at least get the image, because image is just 4 megabytes. So I don't think it's hard for anyone to get the 4 megabyte image in 2 days. Yeah. So, okay. So
Sir,
we'll
one more
disconnect
thing
and-
regarding there was this project course. There was a course project, sorry.
Yes.
So that still holds or what?
The course project actually depends on when the classes resume, because for evaluating the project, I'll have to take a Viva.
All right. All right.
Yeah, so someone mailed me about that, and as long as, so if the semester runs totally in online mode, then I won't be able to evaluate the project.
Okay.
Then we'll see. So we'll always have a situation that suits, or like I said earlier, we'll have a situation which benefits the largest number of students.
Okay.
Okay. So don't worry about that. Just if you have been working on the project, keep working. If you don't have the resources to work on the project from home, don't.
Okay. Good.
Okay, just stay indoors. That's my
Yes.
only concern. Yeah. Okay. Great. So we'll stop here and talk on Monday. Okay. Bye.
Bye.